perfect. Now the record is on. And afterwards, I would like to share my screen. Okay. Okay, you remember that on past lecture, we have ended the lecture by introducing some concepts from the past, okay? And so the first aspect to be recalled are related to the internal action, axial force, shear, and bending moment. And we have already recalled that this kind of quantity should be defined as those quantities that are maintaining the two parts of a beam in equilibrium after an ideal cut, okay? We have already commented about this. So if I have a beam and I make in the beam a real cut, of course, if the structure is statically determined, I will induce a collapse. If I make just an ideal cut, in order to make the two parts in equilibrium, I suppose that two parts are exchanging internal forces, okay? And those internal forces are bending moment, axial forces, and shear forces. We have also to remember, but in order to remember this, I need the blackboard. Where is Antonello? In order to switch for the blackboard, what I have to do? Okay, the person in the, but I have to stop the sharing or not? Oh, so. Honestly speaking, I'm very glad of having again the possibility of working on the blackboard. You know that if we have a beam under some forces, okay, I can take a piece of structure inside the beam. And then if I take a piece of structure inside the beam, the length of this piece of structure is dx. It is possible to have vertical forces on it, horizontal forces on it, and afterwards I have shear on the left-hand side and right-hand side, axial forces on the left-hand side and right-hand side, and bending moment on left-hand side and right-hand side. Generally, if I denote this one as N, this one as T, and this bending moment as M, and I move from this cross-section of a piece along the length of the beam, on the other side, I will have N plus the variation of N, dN, T plus the variation of T, and the bending moment plus the variation of bending moment. Okay? What's happened? Okay, so this is what happens in a beam. I think that in the tutoring you have also seen something like that. The consequence is that when I do the equilibrium, I can say that the variation of the n over dx is equal to this external force, capital small n times dx, and if this one is p times dx. Similarly, I will have that the variation of t over dx is equal to minus p. Okay? And in addition, I will have that the variation of the bending moment over x is equal to the shear. So it comes from the statics. Okay? And it is very important to recall these local equilibrium equations. Why? Because the first equilibrium equation, this one, in terms of the axial force, gives to us a fundamental information. So it's saying to us that in a certain piece of the beam, if there is no variation in the axial forces, in the external axial forces, the axial force n is constant. Otherwise, we have a variation. Okay? Similarly, the shear, we have a variation of shear only in correspondence of an applied force or an applied distribution of forces. And similarly, the variation of the bending moment is related to the presence of the shear. Let's look at the practical consequence of this. Okay? So, I will share again the previous slide. Okay. Perfect. It is very easy to divide our beam in three parts. According to what we have said, if we are looking on the left-hand side, from this point until this point, of course, we have applied forces corresponding to the constrained cross-section and to this cross-section. Between those two cross-sections, the shear is constant, as you can see here. Okay? Similarly, in the central part of the beam, between the application of two concentrated loads, the shear is constant, and in this case, it's equal to 0. And similarly, in the third part, we have that the shear is constant as well. But now, of course, it's negative. Similarly, since the variation of the bending moment, the derivative of the bending moment is the shear, it means that when the shear is constant, the bending moment is linear. Starts from 0 at this point, and it's linear. In the central part, where shear is equal to 0, the bending moment is constant. And in the last part of the beam, where the shear is constant, we have that bending moment is linear. So, when there is a uniformly distributed load along a piece of the beam, along that piece of beam, what we will have in terms of shear, we will have a linear shear, which is increasing by increasing the length of the piece I'm considering, and if the shear is linear, the bending moment has a quadratic law of variation. It's parabolic, okay? But another aspect I have recalled on past time is that the internal forces, bending moment, shear, and axial forces, are resultant because generally, in the case of mechanics of materials, we are accustomed to refer just to the axis of the beam or that column. But let's look at this one. I suppose that this is a bearing column in this row. Of course, I can observe that the axis, of course, is linear, but if I have to look to the cross section, the cross section is a cross section, and this dimension 1 is maybe larger than 1 meter. So we have to consider the real dimension of a cross section, okay? And so the internal forces T and M are resultants. In order to highlight that these internal actions are resultants, we can divide the cross section in small pieces of area delta A, and we assume that for every small pieces there is a normal pressure and a tangential pressure, okay? And so the axial force and the shear are the summation, are the resultants, or this normal and tangential resultant. Bending moment, of course, is the moment of the normal pressures only. Of course, I have already commented on past lecture that from a conceptual standpoint, this kind of definition we are introducing in the equation on the left-hand side from conceptual standpoint are perfect, but you can observe that there is the symbol of an approximation, okay? The approximation stands from the mathematical part. In fact, when I have a summation which is extended to very small pieces whose area tends to 0, that kind of summation is just an integral. From conceptual standpoint, nothing changes. From mathematical standpoint, we have a different symbol, okay? Not more the summation, but the integral, okay? You remember that I have recommended on past lecture to get a look to some concept coming from the mechanics of materials. I have sent to you a link to this book. That book is quite large, so it's not possible to transfer it by email, but if you use that link, you can very easily download that book. And there are several chapters that I recommend to read or to recall. The first chapter, the second chapter, basically related to stress and strain in axial loading, then about bending, then about the shear stress, okay? But now I would like to remember something about that, starting from the axial behavior, pure axial behavior, which is the simpler one, of course. We can recall what happens in axial loading by referring, for example, to a very simple spring, something like an elastic, okay? What happens? Generally, the behavior of the spring or the behavior of an elastic element is characterized by its constant K, okay? When I apply a force F, I have an increase in elongation. If I apply a tensile force, if the force is in compression, of course, I will have shortening, okay? The relationship between the elongation, delta L, and the applied force is a linear relationship for an elastic element. And the tangent between this linear behavior is the constant K of the spring. So when I apply, for example, a force of 1 kilonewton, I will have an elongation of 1 centimeter. Since the behavior is linear, is elastically linear, when I apply a force of 2 kilonewton, I will read an elongation of 2 centimeters, and so on, okay? This is also a good occasion to remember which is the definition of an elastic element and a linear element. Do you remember what is meant as elastic? And what is meant for elastically linear? So what is elastic? What?
It's different origin. There's something that can show us.
I do not understand exactly. Please try to better explain. Yes, but the opposite of rigid is not elastic, it's deformable. Okay? Elastic is a special kind of deformability. Okay? You are studying architecture. So I suppose that every one of you has a rubber. Rubber, something that you use for cancel the pencil. Okay? No one used rubber? So, the rubber is an elastic element. You use rubber, perfect.
When you apply a force,
Yeah?
the beam come back to the initial form of the system.
Exact. When I'm dealing with an elastic element, when I apply a force and remove the force, I will obtain the initial condition by following the same path. Okay? A rubber is an elastic element. In fact, if you try to compress the rubber, after the compression ends, you will obtain the no elongation, okay? But it is not a linear elastic element. In fact, in order to have the same elongation, after you have applied the force, you have to apply an higher force. It's something different from what we are seeing in this diagram, in which if I apply a force of 1, I will obtain a deflection of 1. If I apply the double of the force, I will obtain the double of the displacement. For a rubber element, in order to obtain the double of the displacement, I need to apply more than the double of the force, as you can easily verify with your rubber, okay? But of course, we can do this with an elastic element, with the rubber, with the spring, but also with the bar, okay? With the linear bar like this. I have at the beginning a linear bar, for example, that column, whose length is L0, then I apply an axial force, and then I will measure an elongation or a shortening, depending on the fact, depending on the direction of the applied force, if it is in tension or it is in compression. But generally, what we can measure in the laboratory are forces and displacement. But, for example, I can change the scale of this diagram by doing what? Simply by dividing the applied force by the area of the cross-section. When I divide the applied force by the area of the cross-section, the consequence is that I have a stress, so a local pressure, a distribution along the cross-section of local pressures, okay? And that's the definition of local normal stress. Similarly, I can divide the shortening or the elongation by the original length of the beam. In this case, I will obtain, the local strain, okay? So, generally, since when we are dealing with an elastic element, since there is a direct correlation between the force and the deflection, there is also a direct correlation, a direct correlation between the local stress sigma and the local strain epsilon, okay? So they are proportional. And the constant of proportionality is called capital E. And capital E in mechanics of material is called Young's modulus or normal elastic modulus. What happens is that when I took a small piece of material and then I apply at the opposite end of this small piece of material an internal stress called sigma x, then I will have an elongation in the direction of the force, and the elongation in the direction of the force is simply the stress divided the Young's modulus. But what you can easily observe is that when I'm loading something in a certain direction, in the opposite direction there is a shortening, okay? So also this kind of shortening depends and is proportional to the stress sigma x. Of course, we need to introduce a minus sign here. Why? Because if sigma x is in tension, I have that the strain in the same direction is consistent with the sign of the applied stress. But in the orthogonal direction, if I have a tension, I will measure a shortening. So, a minus sign here. On the denominator, still I have the Young's modulus, but the shortening in the orthogonal direction is lower than the direct elongation. So this coefficient Ni is lower than 1 generally, okay? So in general, when I apply simultaneously two stresses, one in the vertical direction and one in the horizontal direction, in the horizontal direction I will have an horizontal strain which is equal to the stress in the same direction over E minus the stress in the orthogonal direction over E times Ni, and a similar equation also for the direction epsilon, okay? This is of course valid in two directions, but if I want to extend this kind of definition in three directions, I will not have a square element like this, but I will have a cube, so with forces in the orthogonal direction. And so it will be stress also in the zeta direction, and also strain in the zeta direction, okay? Now, let's come back to our beam, and let us assume that there is an axial force applied to the beam, okay? If I'm considering the beam as made as a series of independent fibers, what I expect? I expect that all fibers undergo, for example, an elongation, okay? Or a shortening. The value of the elongation will be equal to the value of stress over the Young's modulus, okay? While the value of the stress is simply equal to the resultant in terms of axial force over the area of the cross section. So in order to remember, I have an axial force applied in the center of the beam, but this axial force is a resultant. In order to pass from the resultant to the local value of the resultant to the local pressure, okay, I have to divide for the area of the cross section. In order to pass to the local deformation, to the local strain, I have to consider in my mind the cross section made as an ensemble, a series of independent fibers. And each one of these independent fibers undergoes a strain which is proportional to the applied stress, okay? Is inversely proportional, so the strain epsilon is equal to sigma over capital E, okay? It's very easy when we are dealing with an axial force, because I pass from the resultant to the local pressures, and from the local pressure, since I understand that the local pressure induces some kind of deformation, local deformation, I can also evaluate the elongation or the strain. Please take care also of the physical dimensions, because the axial force generally is a force, so it's measured in kilonewton, for example. When you pass from the force to the local pressure, what I have called stress, it's the force divided an area, so it's a pressure, and then I will measure it as a pressure, so kilonewton over square meter, or if you prefer, Newton over square millimeter. When I'm going to pass to the strain, of course, the dimension of the strain will be equal to the dimension of the stress over the dimension of capital E. But we have also to remember that the definition of strain is the elongation of a fiber which was originally of length unit. So, the strain, the local deformation, is the variation of length divided the original length. So it's a pure number. I do not measure it in meter. Generally, I measure it in a pure number, and in fact, in the textbook, you can find the strain expressed in, for example, percent or points per thousand. Okay? Of course, we have to remember that there is not only the axial force, but there is also the bending moment causing some normal stresses. In fact, if I go back, please remember this kind of definition. I have defined the bending moment as the moment of the resultants of all these local forces. In fact, it is the summation of sigma delta A, which is the force acting on the small area, times the distance from this axis, okay? And when I pass from the summation to the integral, nothing changes in terms of definition. So it means that similarly to what happens for axial forces, so axial forces generates local stress sigma. Similarly, also the bending moment might generate some normal stress, okay? And since we know that bending moment of a cross-section is associated to a rotation of the beam, okay, of the cross-section of the beam, what I expect is that both normal strain but also the normal stress are linearly depending on the bending moment. So, before I asked you to think to what happens in a cross-section subjected to an axial force, as the cross-section is made by individual fibers, okay? Now, if you think again that the cross-section is made by individual fibers that are connected by a stiff plate, when applied a bending moment, some fibers undergo elongation and some other fibers undergo shortening. And so there is the rotation of the cross-section. But if I have a rotation of the cross-section, it means that when the fibers undergo shortening, there is, in the linear case, a local stress of compression. When the fiber undergoes an elongation, the corresponding stress will be a tension stress. And so there is a linear distribution of stresses which generates a linear distribution of normal strain. And we know that that linear distribution of stresses might be expressed as sigma equal to the bending moment times the distance of the fiber from the neutral axis, from the center of the beam, over the inertia moment, okay? You remember this kind of formula. But if we are dealing with an elastic material, a linear elastic material, for linear elastic material, I have that if I simultaneously apply a bending moment and an axial force, the results in terms of stresses, for example, are the same as I applied first the axial force and then the bending moment. Okay? So the so-called superposition principle holds, is valid. Okay? A first exercise for you in order to remember this. What I'm asking today is that you take this exercise, think it at home, and on next Friday we will discuss the results together, okay? So, I will refer to a very simple rectangular crossbeam, okay? Dimension B and H. And I will apply an axial force which is equal to N and a bending moment which is equal to N times H over 6. What I'm asking to you is to please find the maximum and minimum normal stress. Of course, what I expect is that the maximum and minimum normal stress will be at the opposite ends of the cross section. Please compute it. But so far, I have recalled about the normal stress. But normal stress may arise due to the action of axial force and bending moment. But there is also shear, and also for the effect of the shear, I can have some shear stress. For example, if I refer to two pieces of steel, which are connected by using just one bolt, okay? The upper part undergoes a force which is directed from right to left. The bottom plate is subjected to an opposite force which is directed from left to right, okay? What happens here in this cross section is that the material, of course, of the bolt undergoes to some shear action, okay? And so I will have some shear stress that unfortunately are not the applied shear over the area, okay? The law of variation of shear in cross section is much more complicated. I will recall it in the next slide, okay? But of course, we can also observe a variation of angles which before were angles of 90 degrees, okay? Because before the deformation, this was the shape of this part of the bolt, a rectangular section. After the deformation, after the shear strain occur, I will have that these two angles are no more of 90 degrees. So this value of the variation of the angle is proportional to the shear stress. So I have that from shear resultant, we have that some shear stress tau are arising. And from shear stress, we have a variation of the 90 degrees angle. So a shear strain, shear stress tau and shear strain gamma are proportional one to the other, as in the case of the normal strain and stress. So tau is G times gamma, or if we prefer, gamma is tau over G. G is called shear modulus, like capital E is denoted as Young's modulus or bulk modulus or normal modulus, okay? The problem is that, unlike the case of the simple axial force, in which tau was simply equal to N over A, in the case of shear, the distribution of shear is much more complicated, is given by the so-called Jurasky formula. So the tau, it's equal, of course, to the applied shear force times S star, and S star is a static moment. I will clarify which kind of static moment it is. Afterwards, I have B. B is the length of this part of the cross section. And afterwards, I have J, or iota, which is the inertia moment. Okay, let's try to understand which is the meaning of S star and B. Okay, what we are doing is something like this. Let's have an ideal cut of our cross-section here, or here, or here, at a certain distance of the center, okay? What I assume is that the shear stress is constant along the length of the cut. So P is the length of the cut. In the case of, sorry again, what happened? In the case of a rectangular cross-section, what happens is that P is constant, because when the cut is made in the upper part, in the middle, or in the bottom part, the width of the cross-section does not change. So B, it is constant, okay? But, for example, if we assume a cut here, at this level here, okay, I have an area above the cut, and then area below the cut, okay? If we refer to the shaded area above the cut, the static moment is the static moment of this area with respect to the neutral axis of the bend. So, very easily, since the center of the shaded area is here, basically the static moment S star is equal to the area of this shaded rectangle times the distance between the two centers. The centers of the shaded area and the center of the entire cross-section, okay? Now, if I made the cut here, so corresponding to the lateral surface, to the upper side, the area above is 0. So the static moment is 0. And so shear is 0 if I'm looking at the area above. But when I'm looking to the area below, the area is the area of the entire cross-section. And the static moment of the entire cross-section with respect to its center is 0 as well. Okay? Now, when I'm doing a section at this level, if I'm considering the area above, I will have a certain value of the static moment. When I'm considering the area below, I will obtain exactly the same value of the static moment, numerically, but with the minus sign. Because remember that the static moment, it's a quantity which is characterized by minus or plus sign, okay? So, when we are dealing with a rectangular cross-section, what do we expect? We expect that when we are at the upper bound of the cross-section, since the area above is 0, or if you prefer, the area, the area below, it's equal to the area of the entire cross-section. In both cases, the static moment is 0. But when I'm increasing, for example, the area above the cut, of course, the static moment is increasing. T in this formula remains constant. B in this formula remains constant. The inertia moment of the cross-section does not change as well. Okay? So what I am expecting is that when I'm moving from this border until the center, there is an increase in S star, which induces a non-linear increase in the value of the shear stress. When I'm passing below the center, it is indeed true that I'm adding area, but I'm adding area with a negative distance from the center. And so the consequence of this is that, of course, we have a decrease in the value of the S star value. And so, for a rectangular cross-section in which T is constant, B is constant, and also iota is constant, the variation of the shear stress is given just by the variation of S star. And I have a parabolic law of variation. When we are dealing with an I-beam, and I-beam is very widespread kind of cross-section, for example, for steel structure, as we will see in few minutes and also in the forthcoming lecture. Okay? If we are dealing with the beam like this, basically the acting of the cross-section, the shear action is constant. Okay. The inertia moment, iota, is constant as well. We know for sure that S star will be variable, but also B is variable, because when we are in the upper part or in the lower part of the cross-section, B is the width of the flange, while when we are here along the web, B is the width of the web, which is much lower, of course. Okay? So, similarly to the previous case, we start with a shear stress which is equal to 0 when we are on the bottom part, because on one side we have 0 area, and on the other side we have the area of the entire cross-section. Okay? In both cases, the static moment is equal to 0. When I'm increasing the area of the flange, of the upper flange, which is cut from our section, of course, I have a quadratic increase of S star, and also the shear stress is increasing. When I'm going from the part above and the part below, in the part above, I have that the width is the width of the flange. In the part below, now I have the width of the web, which is much lower. And so I have a sudden increase in the value of the tau, because the static moment from here to here practically does not change. But B in the upper part is larger, in the lower part is very low. And so we have a sudden change like this. Afterwards, when we are moving towards the neutral axis, I'm adding area, and so S star is increasing, and so again I have the maximum value of the shear stress here along the neutral axis. Afterwards, of course, everything is decreasing in a symmetric way with respect to this axis, because the cross section is symmetric with respect to that axis. Okay, now I would like to remember this diagram. We have recalled from past time that when we are evaluating the strength or the resistance of a material, generally we do not refer only to an elastic behavior of the material, but we can refer to elastic plastic behavior of the material. Elastic plastic behavior of the materials means that the material, for example, steel or aluminum, is linear until a certain value of the stress is reached. Okay? This value of the stress is called yielding stress. Okay? And generally it is denoted as Fy. Okay? Generally, from the yielding value of the stress of a real material, I can pass to the so-called K value. The K value is called characteristic value. What does it mean, characteristic? When in structural design we are talking of characteristic value, we assume that there is only, so that there is 95% of probability that the real value of the yielding stress is lower than Fyk. So there is only a 5% probability that the real value is lower than the characteristic value. Okay? So when we talk about characteristic value in terms of strength, it means that we have 95% of probability that the strength is that is larger than that value, and only 5% that it is below that value. Okay? So the design value, the value we use in our computation and in the design of a real building, it's the characteristic value which is further protected by a small safety coefficient. The safety coefficient is gamma S. Gamma S, in order to act as a safety coefficient, basically it should be larger than 1, okay? So, remember, we have an yielding value of the stress for the steel. It means that the sigma epsilon curve is linear until the yielding value of the stress, and afterwards it's constant. Okay? Of course, if we want to pass from the real value of the yielding stress for a steel material, which is larger than this one, than the one that we use in design, okay? A first aspect is related to the uncertainty in the value of the strength. And so we can define a characteristic value, okay? Which means that we are referring for example, to 1 cubic meter of steel, and if I'm going to move in one point, I can assume that there is 95% probability that in that point the real strength is larger than the characteristic value, larger than or equal to, and only 5% that it's lower. In addition, I will protect myself with a safety coefficient. But we can define a linear and elastic plastic behavior of material as something like this. First linear and afterwards constant. I can define this in terms of yielding stress, so real behavior of the material, design stress, okay, or characteristic stress. Why I'm saying this? Because now I'm switching from a behavior which is assumed as linear as the one in mechanics of materials to a classic behavior of a material in structural design. And in structural design, generally we assume, for example, for steel, that the material possesses a non-linear elastic plastic behavior. And so, now my question is, but what happens to stress distribution associated to bending moment beyond the elastic range? So this is the question I would like to ask. And so, what we have to do is to discuss what happens to the strain profile under bending moment. For example, when we are at yielding, the moment at yielding is defined as the value of bending moment that we have, for example, when the two extreme fibers undergo the yielding value of the strain. Okay? When we have this typical behavior, the corresponding diagram of stress is still linear, okay? And it is very easy to evaluate the moment at first yielding, because we know that when the cross section behaves elastically, the value of the strain here is equal to epsilon ypsilon d, for example, and the corresponding value of the stress is equal to F ypsilon d, okay? And so, we know the value of sigma, which is equal to F ypsilon d. We know the value of ypsilon, because ypsilon is h over 2, because we are dealing with the fiber whose distance from the neutral axis is exactly equal to h over 2, and we know the value of the inertia moment. The value of the inertia moment is b h cubed over 12, okay? So in this equation, what we do not know is the value of the yielding bending moment, okay? Because we know that yielding stress is F ypsilon d, and then the ratio between h over 2 and bh cubed over 12 is bh squared over 6. So we do not know just the value of m ypsilon, and the value of the m ypsilon, the yielding bending moment, is simply equal to b h squared over 6 times f ypsilon d. This value, b h squared over 6, is called WL, okay? And so we can say that the value of the yielding bending moment is the value of this coefficient WL times the yielding stress of design. But now, what I want to discuss is what happens when the bending moment is larger than m epsilon, okay? First of all, we are quite sure that it is possible to increase the bending moment beyond the value of m epsilon. Everything starts on a basic assumption. For the elastic behavior of a cross-section, our main assumption is that when a bending moment is acting, the cross-section rotates remaining plane. But when we are in the elastic plastic range, this assumption still holds? That's the question. The answer is yes, it continues on. So, it is possible to assume that when the bending moment is larger than the yielding moment, we have that our cross-section continues to rotate by remaining plane. Okay? But now, for example, let us assume that the profile of strain is this one. What happens? It will happen that the central parts, that in the central parts of the cross-section, all the fibers are still in the elastic range, okay? When we are looking at the fibers at a larger distance from the neutral axis, those fibers undergo a strain which is larger than epsilon d. But the stress cannot exceed the yielding stress. So it is possible very easily to pass from a linear diagram of strain to the corresponding diagram of stress, even if we are in the non-linear range. Because for the fiber in the elastic range, basically we have that the stress is proportional to the strain. When the strain is larger than epsilon d, the stress is constant. And so you can see that the diagram of stresses from triangular becomes something like this, in which the part in the upper part and the part in the bottom part becomes of trapezoidal shape, okay? Of course, we can easily understand what happens at the limit when the neutral axis is completely flat. We have that the upper part is completely in tension and the bottom part is completely in compression in a stress diagram like this. But the resultant of that stress diagram is very easy to compute, basically. Because we know the area of the upper part, which is half the area of the cross-section, okay? And similarly, we know the area of the bottom part, which is half the area of the cross-section. And we know also which is the maximum value of the stress, okay? Which is the yielding stress. And so, very easily, we can evaluate the fully plastic moment, okay? Because the area of the bottom part is BH over 2, half the area of the cross-section, okay? the stress, if F epsilon d, of course, we have a concentrated resultant here and the concentrated resultant in the bottom part, which is the distance between these two resultants. The distance between the two resultants is half the height of the beam. So h over 2. And so the fully plastic moment is equal to b h squared over 4. Okay? Before, for the yielding bending moment, we have had b h squared over 6. Now we have b h squared over 4, which is larger. So this coefficient, bh squared over 4, is called WPL, okay? And the corresponding bending moment, MPL, is called fully plastic moment. Of course, the excursion, the gain of the cross-section by going from the elastic range to the plastic range is given by the ratio between the fully plastic moment and the yielding bending moment. Or, if you prefer, from the value of WPL and the value of WL, okay? So, this coefficient often is called the plastic ratio of the cross-section. Of course, is larger than 1. In the case of a rectangular cross-section, is 6 over 4, okay? 6 over 4 is 3 over 2, which means 1.5. For normal cross-section in steel, generally is not so large, okay? So no 1.5, but a value which is larger than 1, but that is in the range of 1.2, 1.3, something like this. I cannot answer, of course. Okay. So, we are talking about the behavior of the rectangular cross-section. But of course, if we are dealing with the behavior of an I-beam, basically it is the same. And I can also draw a diagram in which on the epsilon axis I can have the bending moment, and on the x-axis I can have the curvature, okay? So we have seen that the profile of strain continues to be linear also in the elastic plastic range. Okay, this rotation is called also curvature, and what happens is, of course, that if we are dealing with a moment curvature relationship on a moment curvature bending moment, diagram, we will have in the elastic range a linear relationship. So, until the value of the yielding bending moment, we will have a linear behavior. When we enter in elastic plastic range until fully plastic range, we have a non-linear behavior like this, and afterwards I have a constant value, okay? Because if you look back at this curve, okay, there is a large interval of value of the strain, epsilon, for which the maximum stress does not change. This means that after reaching this point, there is also a constant field, a constant interval of bending moment in which the bending moment is equal to fully blasting moment. In reality, the fully blasting moment might be also exceeded. Why? Because in reality, there is a part of this diagram in which there is an increase in the stress corresponding to the increase of strain. But generally, we can neglect this kind of behavior, okay? So, from our standpoint, we assume that when we arrive to the fully blasting bending moment, everything stops, okay? So, the moment curvature relationship continues like this. So, we can neglect this increase. Okay, I will show you very quickly some computation. I will give you some other value on next lecture. Of course, since this part is basically related to the behavior of steel cross section, okay? Basically, for steel cross-section, we have IPE, HE, UPE section, and others cross-section. On the next lecture, I will show you basically some details about the industrial production in steel structures. But at present, we have to understand that what we see in the practice is that the industrial production of steel, also of aluminium, includes a large number of I-beams, okay? Basically, for example, you have a lot of manuals in which the dimension of this cross-section are given. For example, for an IPE 200 cross-section, I can obtain from standard textbook or from standard manuals the weight in kilogram per meters, but also the dimension. So the overall height of the beam, which is equal to 200 millimeters. The width of the flanges, in which in this case the width is 100 millimeters. The thickness of the web, the W, which is equal in this case to 5.6 millimeters. The thickness of the flanges, generally the thickness of the flanges for an IPE cross-section is larger than TW, and in this case it's equal to 8.5 millimeters. And the area of cross-section, in this case, 2,850 square millimeters. But of course, I have two main axes, horizontal and vertical axis of behavior passing for the center of the beam, and with respect to this axis, I can evaluate the inertia moment with respect to the two axes, the coefficient we have denoted as WL with respect to Y and Z axis, and also the plastic coefficient, WPL with respect to Y and with respect to Z. Of course, we can observe that the Y direction, so vertical one, is the strong direction of the beam. In fact, the inertia moment with respect to the Y axis, which is the horizontal one, is much larger than the inertia moment in the orthogonal direction. And similarly, WLY is larger than WLZ, and also WPL epsilon is larger than WPL in the zeta direction, okay? Of course, since the value WPL and WAL are only depending on the geometry of the cross-section. In fact, you remember that in the case of a rectangular cross-section, WEL was BH squared over 6, and WPL was BH squared over 4. So they depends on B and H, the dimension of the cross-section. Also, in the case of an I-beam, it depends only on the dimension of the cross-section. Now, the dimension of the cross-section are more complicated, more numbers, of course, because we have H, we have B, we have TF and TW. But WEL and WBL only depends on these 4 numbers. And this is the same also for different kind of cross-section. So in the standard textbook, in the standard tables, we have not only the basic dimension of the cross-section, but also the inertia moments and the coefficients WL and WPL. Of course, we can also very easily verify the numerical value of this coefficient by assuming, for example, that an I-beams consist of 3 rectangles, okay? But of course, we have also to consider that in reality, there are also this part, okay? This rounded part. So the real cross-section is not exactly equal to the superposition of 3 rectangles. So what I expect is that the number we might evaluate by end computation are slightly different, a little bit lower, basically, from I epsilon, WL, epsilon, WPL, epsilon, okay? And this also on different types of cross-section. Here I have summarized several types of cross-section because I will use this for computation. But before concluding my lecture, I would like to try to evaluate, even if in an approximate way, the value of the yielding bending moment in the epsilon and z direction. And of course, the yielding bending moment is simply equal to the value of the yielding stress times WL epsilon, for example. If we're looking to the zeta direction, we will use the same value of F epsilon, but of course the value of WALZ. But another interesting aspect is this one on steel cross-section. If we are, for example, at the end of elastic range, okay? So the acting bending moment is equal to the yielding bending moment, okay? So the stress at the opposite side of the cross section is equal to F epsilon, to the yielding stress, okay? Now, the value of M epsilon is known, but I would like to know which part of this bending moment is carried by the 2 flanges and which part of this bending moment is carried by the web, okay? How we can do this kind of computation? It might be done in a very easy way. We know that the stress distribution corresponding to the value of the yielding moment is a linear stress distribution, okay? So we know that the value of the stress at the opposite ends is equal to F epsilon. But we are interested to the value of the stress sigma star at this point, for example, when we have the connection between the web and the flange, okay? The value of sigma star is the value of sigma at the distance a from the neutral axis. So it will be equal to the yielding bending moment, and we know the value of the yielding bending moment, all times a, and of course we know which is the value of a, okay, over the inertia, the moment of inertia. And we know also from standard table which is the value of the moment of the inertia, okay? Now I have evaluated sigma star by considering the entire cross section, okay? But now I would like to evaluate again the value of sigma star by considering just the web, okay? So if I say that the value sigma star is equal to the bending moment carried by the web, which is the quantity I'm looking for, times A, times just the inertia moment of the web. The inertia moment of the web, of course, is the inertia moment of the rectangle constituting the web, okay? So I also know iota web. Sigma star in this formula will be equal to sigma star in the second formula. What I know in the first formula, everything, because m epsilon is known, A is known, iota tot is known. What is unknown in the second formula? Just m web, because I know what A and the inertia moment of the web. So, by saying that m epsilon times A over iota tot, it's equal to m web times A over iota web, I can evaluate m web. And m web is equal to m epsilon, in this case, times the ratio between iota web over iota tot. Of course, iota web is lower than iota tot. And in fact, what I expect is that what I have denoted as m web is lower, is a part of the entire bending moment. Of course, if I want to evaluate the value of the bending moment in the flange, I will obtain this value as difference between the overall yielding bending moment and the bending moment in the web, okay? Since the bending moment in the web is equal still to ml epsilon times the ratio between iota web over iota tot, I can obtain that this will be equal to this value of the bending moment times the difference between iota tot and iota web and iota tot, okay? And for example, I can very easily evaluate the value of m epsilon L. Why? Okay. The yielding bending moment. The value of the m web and the value of m carried by the flanges, for example, for an IPE cross section made of steel S235. For a steel S235, the yielding strength is equal to 235 Newton per square millimeter. So what I have to do is to take the value of the yielding stress, 235 Newton per square millimeter, which is equal to 235 megapascal, times the value of WL and the value of WL for this coefficient is 194 times 10 elevated to cube, okay? And so I will have this value, okay? So if I'm going from Newton to kilonewton, so I'm passing from Newton per square millimeter to kilonewton per square millimeter. This first number is 0.235 kilonewton per square millimeter times 194,000 millimeter cube. So, of course, I have to multiply millimeter cube times 1 over square millimeter, and so the resultant is in terms of millimeter. In order not to write a number with a lot of zero, I can pass also from millimeter to meter, and then I will obtain 45.59 kilonewton times meter, which are the typical dimension force for length of a bending moment, okay? Now, if I want to evaluate the moment in the web, the moment in the web will be equal to the value I have evaluated of the yielding bending moment times the ratio between iota web and iota tot. The value of the yielding bending moment is 45.59 kilonewton per meter. The value of iota web is the thickness of the web times 2 times the half the 8 of the web. Of course, I have to put this number cube, and I will obtain this number. The value of iota tot is evaluated through the table, and in fact, it is this value, no, not this one, this value here, 1943 times 10 elevated to 4, and in fact, I have this value. Okay, by having this ratio, I will obtain 0.147. So basically, we can see that the moment carried by the wave is only less than 50% the moment, the entire bending moment. So the moment carried by the flange is basically 85.3% the moment carried by the entire bending moment in the elastic range. Of course, I would like to show some other example, but I would like to do this in the next lecture. Before ending the lecture of today, basically I will show you what happens in the plastic range, because we have seen what happens in the elastic range. In the plastic range, I have a situation like this, in which the entire cross-section is with fiber with the yielding stress. So the entire cross-section is plastic. So the upper part is plastic in compression, for example, and the bottom part is plastic in tension. So it is very easy, in this case, evaluate the plastic bending moment carried by the flanges, because it is simple, this resultant, F1, okay, times the twisted, or if we prefer 2 times F1 times this distance A plus TF over 2. Of course, F1 is simply the area of the flange, P times TF times Fy, okay? Similarly, the plastic bending moment in the web is equal to F2, and F2 is equal to Fy times A, the 8 of the half the 8 of the web, times the thickness of the web. So 2 times F2 times half the 8 of the web. And so for the complete cross section, I have just to summing up the 2 bending moment in flanges and in the web, in order to evaluate, if I want to do this, the ratio between the plastic bending moment and the elastic bending moment. You can very easily understand that if I'm starting from the dimension of the cross section in an approximate way, I can easily evaluate the value of the yielding bending moment, the plastic bending moment, the part of the yielding bending moment carried by the web and the flanges, the part of the plastic bending moment carried by the flange and the web. But if I don't want to make any kind of approximation according to the tables, I can evaluate this value by using WL and WPL in the 2 directions, okay? So, I will show some numerical computation on next time. Now, I would like to stop this first part of the lecture of today. As you know, in the second part of the lecture, Dr. Rocco will recall you again some diagram of bending moment, for example. But before stopping sharing and before leaving the room, I would like to ask you if everything is clear, if you have questions, and so on. So, first of all, the students in the real classroom, any question? Okay. It seems that we do not have questions from the real classroom, but we have another classroom with 40 participants at present. So, from the participants, any questions before leaving? So please, if you prefer, you can ask the question through the chat, but as you clearly understand, I prefer to talk a little bit with the students. So if you want to ask question, please show yourself and ask the question. Okay. It seems that there are no question even from the remote audience. So, at this point, I think that we can have 20 minutes of break. Okay, so 12:30. Antonello, please say to me if you want my computer. And so, what I have to do, I can stop record. I have just to pause the record.